Hello everyone, welcome to what will be pre-lecture 16. We're going to continue talking about some acids, bases, and salts. Okay, so last class we discussed how when we put a salt into a solution such as ammonium chloride, it will dissociate into its ions, and then we can individually assess each ion for whether or not it is going to have an effect on the pH. So if we have our first step being that ionic dissociation, then our second step is to examine each of these ions individually and how they would react with water. So ammonium, the positive part, is going to react with water to protonate it to form hydronium and form ammonia. We notice that because we have a weak acid and a weak base present, we know that will have an effect on our pH of our solution. Whereas with something like chloride is the conjugate base of a strong acid, meaning that it is not actually going to perform this reaction, and chloride does not actually have an effect on our overall pH for our solution. Okay, and then same is true for something like acetate. Again, weak base, weak acid, that will have an effect on the pH, whereas sodium, conjugate acid of a strong base, that will not have an effect on the pH, and so we would say that overall this solution would end up basic. So a question you might have had is, what happens if we have something like ammonium acetate, where we end up with two ions that are both weak acids, like ammonium, and weak bases like acetate? So how does this actually affect things if we have a Ka and a Kb value? Essentially, what we do is just find whichever number is bigger. And so if you look at these, ammonium has a very slightly higher Ka value than acetate's Kb value. And so overall, the solution would be very slightly acidic, we would say. And I won't actually have you calculate pH for any of these, because when we combine these equilibria, things can get a little messy. So you don't have to worry about calculating pH here, but it is good to know whether or not something will be acidic or basic based on those values. Okay. The other thing I want to talk about in this pre-lecture is our periodic trends, as well as how molecular shape might affect the acid strength. And so if we think most of the elements that will form acids, at least just pure elements, are shown here. And so if we think about periodic trends, they tend to follow trends based on polarity and ultimately size. And so as something gets more electronegative, it generally becomes more acidic, with the exception being HF. And the reason HF is an exception is because as we get larger in size too, our acids also typically get stronger. But because F, fluoride, is very small, it actually kind of balances those factors out. And so HF is actually just a weak acid. Okay, so just have that in text. Again, more electronegative an atom is, the more polar our HX bond is. That leads to a stronger acid. But we have to balance that when we consider the atomic size. And so HF is ultimately a weak acid, even though F, fluoride, is very polar. It is also quite small. And so if we look at group 6 here, as we go down, we increase our size, our acid strength gets stronger and stronger. Okay? That would also mean something like HI, hydroiodic acid, is going to be a stronger acid than HCl because we have a larger size. Okay? Lastly, also want to talk about oxyacids. So these are acids with basically our hydrogen bound to an oxygen that is then also bound to a central atom. Shown here are the chlorine oxyacids. And so these are very electronegative, and in fact the Ka values are shown here. We should hopefully remember that HClO4 perchloric acid is going to be one of our strong acids. And then HClO3 is basically on that borderline between strong and weak, and then we get weaker as we go down. And this hopefully makes sense to us in that we know oxygen is a very electronegative element. It's going to continue to pull electrons away from the chlorine and away from the oxygen that has a bound hydrogen, as it does that, that means that basically our bond between the oxygen and hydrogen weakens and becomes basically more and more acidic the more oxygens we have. Okay. And lastly, I covered this last week, but it's going to be relevant again in class, and so I wanted to cover it again. Anytime we have a hydrated metal ion with a charge of 3+ or greater, that will also make a solution acidic because when we have that really high positive charge on some sort of metal and water molecules bound to that metal, again, that same thing, that positive charge pulls electrons towards itself, which weakens our oxygen-hydrogen bonds and actually makes it more acidic. So we end up with a metal hydroxide and hydronium in equilibrium. Okay, so that's it for our pre-lecture today. Hope it was helpful. If you do have any questions, please let me know. Otherwise, I will see you in class.